Hello everyone. Today we'll be discussing linear programming problems. Linear programming is a widely used mathematical modeling technique designed to help managers in planning and decision making relative to resource allocation.
To further explain what is linear programming, we will solve two problems from Quantitative Analysis for Management, Chapter 7, number 16 and number 18 using graphical method.
The Dean of the Western College of Business must plan the school's course offerings for the fall semester. Student demands make it necessary to offer at least 30 undergraduate and 20 graduate courses in the term. Faculty contracts also dictate that at least 60 courses be offered in total. In each undergraduate course taught, cost the college an average of $2,500 in faculty wages, and in each graduate course cost $3,000. How many undergraduate and graduate courses should be taught in the fall so that the total faculty salaries are kept to a minimum?
Information received from the problem Chapter 7, number 18, we formulate this linear programming model, which is a minimization problem. Mean z equals to 2,500 x1 plus 3,800 x2 subject to x1 plus x2 greater than equal to 60, x1 greater than equal to 30, and x2 greater than equal to 20. The following inequality constraint should be converted to equality constraint, and then we came up with x1 plus x2 equals to 60, x1 equals to 30, x2 equals to 20. The next step is we should calculate the coordinate points of each constraint. So first constraint is let x1 equals to 0, then x2 equals to 60. If x2 equals to 0, then x1 equals to 60. So we get the coordinate points of the first constraint. By using the same steps from to constraint 2 and constraint 3, we will get the following coordinate points. So x1 plus x2 equals to 60, and its coordinate points is 60, 60. x1 equals to 30, and its coordinate points is 30, 0. And x2 equals to 20, and its coordinate points is 0, 20. The next step is we should plot the points on the graph and make to identify the feasible region along with its endpoints. So this is the line for constraint 1, and this is the line for constraint 2, and this is the line for constraint 3. Point A is the intersection of constraint 1 and constraint 2, and point C is the intersection of constraint 3 and constraint 1. So these are the endpoints, and this is the feasible region. To solve the coordinate points of point A, we used elimination method of the intersection of constraint 1, which is this one, and constraint 3, and which is this one. So x1 is equals to 40 and x2 equals to 20, which is the coordinate points of point A is 40, 20, while the coordinate points of point C is x2 equals to 30 and x1 equals to 30, which is 30, 30. Since we already obtained the coordinate of the endpoints, we substitute the endpoints in the objective function so that we will get the minimum faculty wage. So we substitute here the 40-20, which is 160,000, and while the 30-30 here, which is 165,000. We chose the 160,000 since the objective is to minimize the total faculty salary.
A candidate for mayor in a small town has allocated $40,000 for last-minute advertising in the days preceding the election. Two types of ads will be used: radio and television. Each radio ad costs $200 and reaches an estimated 3,000 people. Each television ad costs $500 and reaches an estimated 7,000 people. In planning the advertising campaign, the campaign manager would like to reach as many people as possible. Machi has stipulated that at least 10 ads of each type should be used. Also, the number of radio ads must be at least great as the number of television ads. How many ads of each type should be used? How many people will this reach?
So we came up with an LP model. Maximize Z is equals to 3000x1 plus 7000x2 subject to $200 x1 plus $500 x2 less than or equal to $40,000. x1 plus x2 is greater than or equal to 10 and x1 minus x2 greater than or equal to 0, then the inequality constraints. So we let x1 and x2 are the two variables that represent the number of radio ads and television ads respectively. So for the objective function, each radio ad cost $200 and each television cost $500. Meanwhile, each radio ad reaches about 3,000 people and television reaches 7,000 people. Therefore, the LP problem is Z is equals to 3000x1 plus 7000x2. So for the constraints, first constraint is 200x1 plus 500x2 is equals to 40,000. So we let x1 is equals to 0, then 500x2 is equals to 40,000. So your x2 is 80 and the coordinate is 0 and 80. For x2 is equals to 0, then 200x1 is equals to 40,000. So you have x1 is equals to 200 and 200 is equals to 0 is the coordinate, and for the first constraint you have 280. And for the second constraint, you have x1 plus x2 is equals to 10. We let x1 is equals to 0, then x2 is 10. So you have 0 and 10 points. x2 is equals to 0, then x1 is equals to 10, 10, 0. You have 10 points. So in here, the feasible region or the feasible points are shown. We have here points A, B, and C. So point A is the intersection between constraint 1 and 3. Point B is the intersection between constraints 2 and 3. And intersection 2 and 1 is for point C. So we have here the coordinate points. For point A, we have 400/7 and 400/7. Point B is equals to 10 and 10. Point C is equals to 175 and 10. So by algebra, it is solved using elimination method. So since we have obtained the following points or values, so we are going to solve individually to the objective function the following points from point A, point B, and point C. So we have here the objective function, which is maximization or maximize Z is equals to 3000x times 400/7 plus 7,000 times 400/7 for point A. So we have 571,429. And for point B, 3,000 substitute 10 plus 7,000 times 10, we have here 100,000 as the value for the maximization for point B. And for point C, 175 and 10, 3,000 times 175 plus 7,000 times 10, we have 595,000. So we choose 595,000 for point C as the optimal solution because the objective is to maximize the people. Therefore, the optimal solution is to use 175 radio ads and 10 television ads, and then the maximum people would be 595,000.